Okay, let's do a few more examples of predicting the products of chemical reactions, specifically chemical reactions involving two solutions of ionic compounds, because those products using what's called the cation swap method. And the idea here is that we have a solution of an ionic compound, such as barium chloride. In this solution, you actually have barium ions that are floating around freely, and you have chloride ions floating around freely. Likewise, in sodium phosphate solution, you have sodium ions that are floating around, phosphate ions that are also freely floating around. And when you combine this solution with this solution, then the cations of this solution, the barium ions, they have an opportunity to react with the anions of the other solution. Likewise, the cations of this solution have an opportunity to react with the anions of the first solution. So to predict what those products may be, or the formulas those products may be, we use the cation swap method, which means that we take our reactants, barium chloride and sodium phosphate, and we simply write down what those ions are. So we have barium, and then we have chloride. Just simply the identities of two components, the cation and anion, not worrying about the subscripts. The subscripts indicate that within barium chloride, because the charges, we have to have two chloride ions for every one barium ion. So the identities are barium ions, chloride ions. Likewise, we have sodium ions, and we have phosphate ions. So this is the identities of the ions in the first solution. These are the identities of the ions in the second solution. And then we have our cations as well, which means that the barium ion is no longer paired with chloride. It's now paired up with the phosphate, and the sodium is now paired up with the chloride. So consequently then, we now have barium with phosphate. That's one new combination. So barium and phosphate, Ba and PO4. Barium is +2, phosphate's -3. We can use the crossover method, determine then that formula of barium phosphate would be Ba3 and PO4 2. That's the formula of one possible product is Ba3 PO4 2. And in the second possible product, there would be sodium and chloride. Sodium is +1, chloride is -1, equal opposite charges. Consequently, it's going to be a 1-to-1 ratio. There's simply NaCl. And that gives us now our products, our two possible products, barium phosphate, sodium chloride. To finish balancing the equation, of course, we need to change some of these coefficients. So perhaps a 3 sodium, that's 3 sodium here. We have, well, let's actually back up a little bit. Let's balance the phosphate first. So we have 2 phosphates versus 1 phosphate. Let's put 2 there. We have then 6 sodiums versus 1 sodium. So 6 here, 6 chlorides versus 2 chlorides. Let's put 3 there, and then 3 bariums, matches 3 bariums. So now we have our first equation, equation A here. The finished equation, we predicted the possible products of this reaction between barium chloride and sodium phosphate. Let's do the same for equation B. So again, potassium carbonate and silver nitrate. Potassium carbonate exists as potassium ions, carbonate ions. Silver nitrate exists as silver ions and nitrate ions. So we have potassium ions and carbonate ions. We also have silver ions and nitrate ions. Using the cation swap method, silver is now paired up with carbonate. Potassium will now be paired up with nitrate. We then get our two possible products. We have silver and carbonate. So Ag +1, carbonate -2. Using the cation, using the crossover method rather, realize that in order to be balanced or the electroneutral neutral compound, we need to have 2 silver ions for every 1 carbonate. So we have Ag2CO3 is one form of one possible product. And the other possible product then will be potassium with nitrate. So we have potassium +1, nitrate -1, 1, both equal opposite charges, so therefore a 1-to-1 ratio. So just potassium nitrate. So those are the formulas of our two products. To balance the equation, notice we have 2 potassiums versus just 1 potassium. So I need 2 here, 2 nitrates versus 1 nitrate. So I need a 2 here, 2 silvers next to 2 silvers, 1 carbonate next to 1 carbonate. And finally, our last example, a solution of magnesium acetate plus combined with a solution of potassium sulfate. So magnesium acetate, in that solution, it just exists as magnesium ions and acetate ions. Notice that in this example, how important it is to know, or at least recognize those high atomic ions. You see those a lot. And then we have potassium sulfate, which exists as potassium ions and sulfate ions. Using the cation swap method, potassium could potentially now be paired up with the acetate ions. Magnesium could potentially then pair up with the sulfate ions to give us then formulas. Potassium and acetate. Potassium +1, acetate -1. Notice that, like we've seen before, equal but opposite charges, +1, -1. So it's going to be a 1-to-1 ratio. And the second product then is going to be magnesium with sulfate, Mg2+, SO4 2-. Also notice equal and opposite charges. So also going to be a 1-to-1 ratio. MgSO4 will be the formula then of magnesium sulfate. Finally, to balance this equation, notice we have 2 acetates versus just 1 acetate. So I'll need a 2 here. They give me 2 potassiums, which matches the 2 potassiums, 1 sulfate, 1 sulfate, 1 magnesium, 1 magnesium. So now we have 3 equations where we predicted the formulas of the possible products between the reactants of these 2 substances using the cation swap method.